Hey, AP Stats, Mr. Hayes here. I'm going to run through the Unit 6 free response questions. I'm going to try to keep this down to a half hour, so hopefully I can get through all four. This is the first time I've actually used a combination of Cami and my recorder because I actually found a good stylus that I think will work. So hopefully you'll be able to read my writing. If not, we'll go back to the old way. So first of all, let's get through and get to the first question. From 2018, number 3, approximately 3.5% of all children born into a certain region from multiple births. Now, of the children born in that region who are multiple births, 22% are left-handed. Of the children born in the region of single births, 11% are left-handed. What's the probability randomly selected children born in the region are left-handed? Now, this whole unit, remember, is talking about probability and how to tie it into most of the statistical stuff that we're doing. Now, if you looked at the answer key for this, it looks really, I guess for lack of a better word, kind of crazy. It was all of this, da 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 da. Now, there's a couple different ways to do it, and I'll show you both. The way that they kind of talk about it is they're going to say, okay, you have 3.5%, 30.35. I need another zero in there. All right, let's try this again. 0.035. So you've got a 3.5% chance that they're going to come from a multiple birth. Of those multiple births, 22% of them are multiples. Can I close it? Okay. And then we're also going to talk about everybody else. Everybody else would be in that 96.5%. And 11% of those are left-handed. So in terms of writing this out, I would recommend at least, you're probably best off, I mean, that's fine there. You're probably better off, let me check the key here really quick. You have to connect the results into a formula. And so like you're going to have to say something like, you know, P of L is equal to the probability of left-handed, probability of getting a multiple times the probability of being left-handed, given that you're a multiple, or given the probability of that if you're left-handed, you're multiple, plus probability of a single birth, plus the probability of left-handed, given the fact that you're a single birth, et cetera, et cetera. And if you do this, you're going to go ahead and get just over 11%. Now, the way that I would be tended to kind of prone to do this, just because of the way that I think, and I think we talked about this in class, would be like this. Hello. Anyway, I'm trying to... I would be more tempted to do this. I would kind of be saying, you know, birth, just do a tree diagram. Okay. So multiple, wow, that's an ugly multiple. So, you know, multiple, single, and so then you'd have a point. So you've got a 0.035 chance of going this way, 0.965 chance of going that way, and then you're going to say left-handed, right-handed. And what this does is two things. A, it's a little bit more, I think it's a little bit more natural in terms of understanding what's going on. I think also it's a little bit, you don't have to come up with all of this. Okay, it's very clear by the tree diagram that you know what you're doing, that you're figuring out where things are going. And the two that we want are right here and right here. So then again, you'd have, and I would write this out. And then that. Wow. Mr. Hayes, you need more practice with this. Et cetera, et cetera. And then you're going to get 0.11385. So again, the whole idea there is that you're going through and demonstrating that you know where the numbers are coming from. If you just put those numbers at the top from part A, that's not going to be enough. They're not going to give you full credit on that. Okay. Now for part B, what's the probability that a randomly selected child born in the region is a child from a multiple birth, given that the child selected is left-handed? All right, so this right here is that number that we just came up with, at 0.11385. Okay, and so that's the given. So again, remember your probability of a multiple given the fact that they're left-handed. Okay, that's the probability of their multiple and left-handed over the probability of just left-handed. And so the probability of being left-handed, we know, is that. And the probability that they're both, and you've already, oops, I meant to scroll up, sorry. The probability that they're both, you basically have right here. And that's one of the benefits of actually writing out some of those numbers. But anyway, you still basically have the work done for you. You just have to go through and actually write it down. Oops, too much. I was thinking about the 385 in the bottom. And then 0.22. And so again, if you show your work, then at least that way, if you make a mistake, they know where the mistake happened. So anyway, that's going to lead you to point approximately equal to 0.676. So that's a probability of multiple given the fact that you're left-handed. So if you're left-handed, I missed a 0 there. Those of you joining us from elsewhere in the country are going to be like, why would I ever go to that school? It's a wonderful school. Plus, obviously, I'm more than willing to show you that I make mistakes. Okay. Now for part C, it's a little different. Let a random sample of 20 children born in the region will be selected. What's the probability the sample will have at least 3 children who are left-handed? Now, this is going to, again, one of those key concepts from this unit. So the probability that X is greater than or equal to 3, okay, remember, is equal to basically 100% minus whatever you don't want. So in this case, you'd have this. So your question is, do you either want to find the probabilities of 3, 4, 5, all the way up to 20 children, add them all up, or do we want to find the probabilities of having 0 children being left-handed, 1 child being left-handed, etc.? So for that, what you're going to end up doing is this. So we got 1 minus. So we got, remember, 20 choose 0. And that's going to be times point. So again, what's the probability of being left-handed? Probability of being left-handed is that 11385 number. And we've got 0 of those times the probability of not being left-handed, which is also known as being right-handed. And then you're going to say 20. And then we're going to subtract off from there 20 choose 1. And remember, these are basically staying the same, but what you're doing is that you're just adding in all of this. And again, remember, this number here, let's see if I can find the highlighter. Hey, no, I'm not signing anything. Markup, that's what I want. This part right here, okay? The first part is telling you what's the probability of getting a left-hander and the probability of getting a right-hander, right? But again, that's only for one condition. So like right there, that would be for having that left-hander be either first or second or third. And you have to make sure you take into account that that left-hander was either the first child you picked all the way up to the 20th child that you picked. So anyway, come on. All right. And then 20, choose 2. This, by the way, is as ugly as 0 that you will ever see. And then same thing. And remember, it's not showing work, it's demonstrating that you know what you're doing. So when you do all of this, you're going to get 1 minus right around 60%. So then you're going to end up with, actually those should be approximately equals. Will it matter? Yeah, I would guess probably not, but as we've talked about all year, why tempt fate? And then again, it would probably be not a bad idea to write out something to say blah, 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 blah. All right. Next problem. 2016. Come on. Model rockets. I'll tell you a story about model rocket engines one time, but I won't do it now. Let's just say it has to do with the toy car, and we'll leave it at that. So the whole, again, same idea. Blah, 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 blah. So let's just jump down. I'm going to assume that you read the question. The failure rate of the super igniters is 15%. What's the probability that the first 30 super igniters used in the testing process will successfully launch? Well, before you ask, yes, it does seem as simple as it is. Okay, so failure rate is 15%. So that means that success is going to be 85%. So that means you're oh my goodness. This is why you practice with things first before you go on tour, Mr. Hayes. Or Mr. Hayes, if you just slow down a touch, I bet you that would help too. All right, so we're doing the first 30. Oh, I was right. So that's all you really need to do. And so go ahead and you plug that in, and then that's going to be approximately 0.0076. So then again, you would just say probability of no There I am, writing too fast again. I know, you'll miss me in college. Okay, so there's your probability of that. So now, given the first 30 superigniters are successfully launched, what's the probability that the first failure occurs at the 31st or 32nd superigniter? If the failure test rate of superigniters is 15%. So again, you're going to kind of do the same thing. So then the question here becomes, what is the first? So what's the chances of, you've already had the 30 go fine. Remember, there's no bearing. Those first 30 things have no bearing because they're all independent. So the probability of a failure on 31 is just 15%. Okay. And we're going to add that to what's the probability that if 31 was okay. Oh, it says or, so you're just going to add. So the probability of a failure on 32 is going to be the 0.85, the fact that, okay, everything went okay the first time, and it failed the second time. So you're going to get those numbers, this number here, so this is going to be 15%, plus this is now going to turn into 12.75%. So the probability that you're going to fail on 31 or 32 is going to then be 27.75%. Okay? The catch there is that people are going to want to use, where's my markup? Hey, there we go. People are going to want to use this. Oh, wait, I don't need that. Anyway, so they're going to want to use that first number down in the second one, and you don't have to. So be careful of that. Given the first 30 superigniters successfully launch rockets, is it reasonable to believe that the failure rate of the superigniters is less than 15%? Explain. All right. So now this is tying in stuff that we haven't, if we were going through this at the time, we were just getting into that idea of, is it significant enough? And so what you need to go through here and talk about how the probability is equal to 0.007, what do I have? 0076. That is less than, you can either say 1% or 5%. And those are kind of our significance levels. Those are alpha values. So you would just say, you know, since alpha is, pick a number, doesn't matter, and blah, 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 is less than 0.05. And then you'd go on and say, and I'm not going to write it down for the sake of time and for the sake of you laughing at my writing, that you would say it's reasonable to believe that the failure rate is less than 15%. Okay? All right, 2015. Dun, dun, dun. These are going to be kind of similar. This first one's actually kind of nice because, again, it starts off simple. What's the probability that at least one ATM is working? Well, the probability of at least one. So again, number of ATMs working in the mall when it opens. So probability of X being greater than or equal to 1. You can either have it be 1 minus the probability of 0. You could also just go 0.21 plus 0.40 plus 0.24. Either way, you come up with 85%. Don't panic if you get a question like that. If it seems too simple, don't make it harder. Especially if it's the first part of a problem. Okay. What's the expected value? Now remember with expected value. Okay. Hello. With expected value, what you're trying to do is saying how many are working. So again, remember that is probability times value. Okay, so your expected value of X, so how many ATMs do we expect to be working when the mall opens, is going to be, okay, 0 ATMs is going to be times 15%. 1 ATM is going to be times 21%. 2 ATMs is going to be 40%. And 3 ATMs is 24%. Now, before you ask, a mall is a place. It's an enclosed area that has lots of stores. You can walk inside and go from store to store and do shopping. Ask your parents about it. Maybe grandparents as well. So anyway, if you do that, you should come up with an expected value of 1.73. Label it machines, ATMs, whatever. What's the probability that all 3 ATMs are working when the mall opens, given that at least 1 ATM is working? All right, so what's the probability that we have 3 given 1 is working? Okay. You know what? We should probably write that a little bit nicer. So what is the probability that X equals 3, given that X is greater than or equal? Whoa. That was not my fault. No, it probably was. All right. So for this, we got some options here, right? Now, again, nice thing here, we kind of already done a lot of the work. Okay. So this is going to be the probability that X is equal to 3 and X is bigger than 1, which is the same thing, divided by probability that X is bigger than 1, or bigger than or equal to 1. Now, we've already found that up here, right? That's what we have right here. So the probability of having at least 1 machine working is going to be 0.85. The probability that we have 3 machines working, given the fact that 1 is working, is still just going to be this number up here, the 24. So 0.24. So we're going to get an approximate of just over 28%. And the last question, given that at least one ATM is working when the mall opens, what would be the expected value of the number of ATMs that are working to be less than, equal to, or expected value from Part B? Explain. All right. So if you eliminate, think about what's going on. What universe, if we're looking back up here, what universe are we living in? If you know that we have at least one ATM working, what's the universe that we're working in? It is this area here, okay? So the total that you're dividing out by, okay, your expected value, instead of multiplying the 1 by 27, this probability is going to become, so that's what, 85%. So this probability now is going to be 0.21 divided by 0.85. So that's going to increase. This here is going to be 0.40 divided by 0.85. This up here is now going to become 0.24 divided by 0.85. And then you're going to multiply that by the expected values. Now, in terms of what the question is asking, you don't necessarily have to demonstrate what the number is, because notice it is saying less than, equal to, or greater than expected. So what you need to say here, okay, is something to the effect of, by omitting 0 ATMs working, or 0 ATMs, let's say probability. So 0 ATMs, the probabilities of 1, 2, or 3 ATMs all increase. The expected value would increase as well. And that's it. Ta-da. So again, that's an example of one where you can probably reason your way through it. You may want to take a look at it, maybe play with some of the numbers, but you don't have to go through all the numbers in the problem itself. Okay. Last problem, where are we at time-wise? 22 minutes. Okay, we're fine. So let's take a look at 2013. Ooh, eggs. Yay. So a full carton of grade A eggs, randomly selected. Blah, 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 blah. What is the probability that all randomly selected full carton grade eggs will weigh more than 850 grams? Okay, this is just basically z-score. Okay, so you're going to say, wait a second, I've got 850 grams. I want that. I'm going to compare it to my mean, which is 840 grams. Ooh, if only there was something to standardize it. I'm going to clean that up. My apologies. Oh, wait, we do. Standard deviation is 7.9. So when you do that, you're going to get, it's approximately equal to 1.27, either on your calculator or on the z-table score. You're going to go ahead and throw that in. So the probability that your weight is bigger than 850 grams is going to be equal to the same thing as the probability of your z-score being bigger than 1.27, right? Because we want to know this is bigger. And so you're going to end up with a number that is just around 10%. Okay. So not totally atypical. Part B. The weights of the empty cardboard container have a mean of 20 grams and standard deviation of 1.7. Is it reasonable to assume it is reasonable to assume independence? Basically, this is saying, all right, so what is the weight of a singly randomly selected egg? All right. So it makes sense that the entire weight of the package, I'm tired of red. So the weight of the entire package is going to be the package itself plus egg number 1, egg number 2, egg number 3, all the way up to egg number 12, right? Now, all those expected values are going to be relatively the same because we're going to say they have the same, all the eggs have the same mean weight. Okay. So since those all have the same mean, you can basically go through and say, all right, this is going to be, so the expected weight is going to be the same as the expected mass of the packaging plus, wow, I think it's, oh, I think my hand's trailing. That might be part of it. Plus 12 times the expected value of your eggs. Because you already have 12 of them. I mean, we have 12 of them. The means are going to be all the same. They're independent. Different hens are going to be whatever. You got the idea. So then from here, it's just algebra, to be honest. So what ends up happening then is that since we've got a average weight, what was our average weight again? 840. Okay. Go in. This is 840. We have an average weight of 20 grams here, plus 12 EX. You're basically going to go through and say, all right, well, 820 grams is for the eggs. I've got 12 of those. So I've got that, and I'm going to come up with about 68.33 grams per egg. Now for standard deviation, a little different. Remember, whenever you're messing with standard deviation, you have to mess with variance, which means that everything we're going to do, we're going to have to square. Long story short. Now, the math is very similar to what we did up here, but instead of doing it with means or expected values, it's going to be the same with the standard deviation. So, long story short, your variance of your weight is going to be the same as your variance of the package plus 12 of your variance of your eggs. Okay, so now we know that the standard deviation of the weight was 7.9 grams. We have to square that to change it from standard deviation to variance. Standard deviation of the packaging is 1.7. We've got to square that. Okay, so when you do that, what you're going to end up with, plus then I've got 12 of these, right? 12 variances of X. So then you're going to do the math. You're going to subtract everything off. It's going to be amazing. It'll be wonderful. So then you're going to end up with, what is this going to turn out to be? You're going to basically, so the variance for an egg is going to be your 7.9 squared. I'm going to take, that's essentially going to the other side. So I'm going to take off that variance of the package. Mr. Hayes' fat hands, once again, cause problems. And I'm going to divide that all through by 12. So again, don't forget to square those things out. So you're going to end up with a variance per egg of 4.96. And that's, remember, we want standard deviation. And so it's going to be the square root of 4.96. So that's going to be approximately equal to a variation of 2.23 grams. So standard deviation of an egg. Okay. So that's that. Hopefully that helps. If you have any questions, shoot me an email. But I think that hopefully will explain, I mean, obviously it works the work, but hopefully I've given some background onto it so that you find that helpful. And I'm just hit 30 minutes. So we'll talk to you later. Thanks.